are the outline, introduction to the NDT and different kind of methods and what is an ultrasound and what is the basic principle behind and what are the different types of transducers and what are the type of wave propagations and what are the techniques involved. So what are the different kind of techniques we will use in ultrasonic testing and what are the equipments like flaw detectors, D meters, like calibrations and inspection applications. So we'll see the real-time applications in ultrasonic testing. What are the real-time applications? How this ultrasonic testing will helpful. And finally, advantages and limitations. And at the end, we'll see the advanced techniques like phase radar ultrasonic testing and time of flight diffraction. First one is, what is a non-destructive testing? Actually, why we are going for non-destructive testing, even though we have a destructive testing, but why we are going for non-destructive testing? The main advantage of non-destructive testing is non-destructive testing is a process of inspection, testing, and evaluation of material without affecting its functionality, without damaging the material. If you see in a destructive testing, we will cut the material and we will test it in a laboratory. But most of the practical challenges, we have to do the in-service inspection without damaging the functionality. There, NDT play a major role, non-destructive testing. If you see in the screen, you can say various methods like UT ultrasonic testing, a guy is holding the probe, and radiography testing using the radiation as a medium to, to, to profiling and visual inspection. Here you can see this guy is holding the boroscope and penetrate testing for measuring the any surface cracks. So ultimate aim is indirectly we are non-destructive technique is like an indirect way of measuring the defects or whatever abnormalities. Accordingly, as per our requirement, like if we are looking for surface indications, we will do some setup. We will see in upcoming slides what are the methods we will use for surface inspection or internal inspection. So basically, inspection, like a process of inspection without damaging its functional properties. That's the main motto of the non-destructive testing. And next slides, we'll see what are the methods are available in non-destructive testing. And these methods are divided again into two categories, which are this method, particular methods will detect only surface and subsurface, and some methods will detect only internal defects. If you see in left side, visual testing and penetrant testing and magnetic particle testing and guided wave eddy current. These are like mostly used for surface inspection and subsurface. This magnetic particle testing is will use for surface and subsurface. But if you see in a radiography and ultrasonic inspection, these are mostly we will use for internal defect detection with internal inspection. We will see clearly, and my today talk is basically on ultrasonic testing. So why it is ultrasonic testing is more every inspection method has its own advantages and limitations, but in this ultrasonic has a high importance. Let's see one by one. These are the basic methods, and even other methods also like as sir told, like thermography and acoustic emission based on the applications. This next word is like introduction to the ultrasonic testing. So what is an ultrasonic testing basically? If you see, for example, I want to tell you a practical example. So if you put a stone in the pond, it will generate a sound waves, like sound waves you can see in the pond. It's nothing but a sound waves. But basically, what I'm trying to say that ultrasonic is a higher frequency. It's like more than 20 kilohertz frequency we will use to examine the materials inspections. And either that ultrasonic inspection can be used for flaw detection, like flaw detection in the material, evaluation or dimensional measurement. If you see here, there's a pictorial explanation. Here is the sample, and one is probe is there. And we are sending the ultrasonic signal. In upcoming slides, we'll see why we are using why we are using the ultrasound and how what is the basic principle. Here I'm just explaining what is an ultrasonic testing. Yes. And before going to the basic principle of ultrasonic testing, once we should aware the basic terminologies like what is a sound and what is the frequency, what is the wavelength. I I must know everybody aware about it. But let me tell you in a short way. Okay, if you see this acoustic spectrum, this 16 Hz to the 20 Hz kilohertz, it's called a audible range. And after 20 kilohertz, it's ultrasonic range. So in this ultrasonic range, so the basic parameters will include like wavelength, and frequency and velocity. This wavelength is nothing but it's a distance required to complete an entire cycle. Am I audible? Hello?
Yes, yes, you are audible.
Please.
Yes, sir.
If you see this sinusoidal function, if you see that the distance is required to complete in one particular cycle, it's called in one particular wavelength. And if you talk about a frequency, number of cycles per second, this particular second, suppose this particular is in one cycle per second, that's 1 Hz, nothing but. So from this diagram, you can see maximum amplitude and wavelength and frequency. I'm not much discussing. These are the basic parameters required to understand the sound. And if you see then relate this relation like lambda is equal to V by F. And regarding to velocity, how quick the sound travels, especially in ultrasonic, the two parameters are very important: velocity and frequency wavelength. These three parameters are very important, like frequency and wavelength alternatives. And if you see that what actually it is depending on the elasticity and density of the material. So always the density, if it is very, that automatically velocity also will change, since this product of density and elasticity. If you say velocity in the material, the particular materials always it is constant only. Suppose if you take the steel, longitudinal velocity is 5960 meter per seconds. Mostly we will use this velocity for testing the steel materials. For water 1470, for air 330 meter per seconds. Basic idea is like we should we should aware about this parameters like wavelength, frequency, and velocity. And in this slide, mostly my concern is what is an ultrasonic testing? What is ultrasound? The ultrasound is nothing but above 20 kilohertz at frequency. The frequency is above 20 kilohertz. In upcoming slides, we'll see the basic principle behind an ultrasonic testing. And as we know, but why, if you see the spectrum, we have a lot of range of frequencies, but why we are mostly concentrating on ultrasound frequency? This is the one question. Okay. For my explanation, why we are choosing the ultrasound, because the wavelength is comparable to the critical dimensions of the discontinuity. So if you see that particular range, that frequency range, that if you are converting to longer, if wavelength, that wavelength is matching to the our critical dimensions. That is the main motto. We are looking that particular ultrasonic spectrum only, since it is matching with our requirements, detection capabilities. And generally, we will use the frequency in between like 0.5 megahertz to 12 megahertz. This is our most preferable. And mostly we'll use 5, it depends on the application. Suppose for higher frequencies, we have a better resolution. For lower frequency has a better depth. It depends on the wavelength. With a higher frequency means lower wavelength, it can detect a even small indications also. If it is a higher depth, we have to use the lower frequencies. It can travel a long distances. This wavelength is more. Here we'll come to know that why we are using the ultrasound only from the particular spectrum. We have a range of spectrums. Coming to the basic principle, in what principle it is working, ultrasonic signal. Basically, so if you see three parameters is always involved in this. If you see the flaw detector, if you can see right side, this one is the ultrasonic flaw detector. This one is the probe. It's like if you see this is our brain, this one is the eye. Without this probe, it cannot see the inside material. Okay. So the purpose of probe is to generate the ultrasonic signal. It's like it contain the upcoming slide. We will see what is the probe and what is the mechanism. But simply I'm telling that the ultrasound is transmitted into the material through the probe, and when it is reflecting, and this reflected waves are inspected. So in a simple way, the amount of reflected or transmitted energy can be detected and provide the information about the size of the reflector. If you could see the screen, this one is the probe. When it is emitting, when it's sending the signal, here there is no defect. These are the defect indications. These are the defects. If you see the red one is the defect. If it is firing here, here there is no defect. So here you will not get any indication, flaw indication. Only you will get input signal and backward. When it is about to reaching the defect indication, you will get an echo based on the how much energy is reflecting. Basically, if you see this ultrasonic flaw detector, x-axis is the time or distance, or y-axis is the amplitude. So when we are detecting the defect signal, we are trying to analyze in a flaw detector. We'll see the echo dynamics. How this echo dynamics. Based on the echo dynamics, we will decide whether what kind of characteristics. It's like a fusion or porosity. Based on the echo dynamics, we will judge it. Basically, the amount of signal we are receiving, based on the receiving signal, we will measure, and the travel time of the sound can be measured. This provide the information on the distance the sound has traveled. So the basic principle. Basic principle is like every material has its own impedance. When it is changing the medium, it changes the impedance. When it's changing the impedance, suppose it has some particular velocity, and there is any like defect, it changes automatically. When it is detecting, its energy will reflect back and will reach to the probe, and it will reflect it on the flaw detector. And based on the time travel, we can measure the time travel. Based on the time, we can say suppose it is taking, suppose it is 15 mm, so it will take the less time compared to this defect signal. Defect signal take the less time. So based on that, we can see that distance, how much distance it is coming, how much depth it is coming. We can see that clearly on the flaw detector. And regarding the couplant is like a medium. If you see in this block diagram here, we have applied a couplant agent. This is majorly we are using to eliminate the air gap. The probe should be proper contact with the test material. In order to avoid that air gap, we will apply different couplants. We have a different mediums like water, kerosene, grease, glycerin. It can be used as a couplant. The main advantage of couplant is to remove the air gap in between probe and surface area. Generally, the best is like glycerin. It always depends on the application only. Sometimes in immersion systems, it is water only. It depends on the applications. Most probably, the basic idea is couplant is a medium we will use to remove the air gap between probe and surface of the object, inspecting object. And how this ultrasound is generated? Basically, this ultrasound is generation. Basically, it involved a transducer. If you see an ultrasonic probe, there is a piezoelectric crystal. What it will do when we are sending the electric energy, like voltage, it will generate, it will convert electrical energy into mechanical. It's like vice versa. So if you see any electrical course, when it is hitting, for example, it is hitting any object, suddenly airbags will open. There is a artificial electric sensors. It will absorb the mechanical and it connect into electrical signal and airbag will open suddenly. The same way here also that here we are using for to generate the sound ultrasonic waves. That's the reason we are using piezoelectric crystal. This is the basic setup of piezoelectric crystal. The same crystal is a capable of transmitting and receiving the sound energy. If you see this is the like electrodes. This one is the piezoelectric crystal. This is the banking material. It's like a damping material. It will absorb the unwanted noise, unwanted signals. So banking materials, epoxy. This is a basic structure of the ultrasonic probe. See here, electric signal is sending and piezoelectric crystal it's generating ultrasonic wave. This is a basic structure of an ultrasonic transducer. We have a different kind of ultrasonic probes, and we will use this different ultrasonic probes based on the applications. Generally we have like basically straight beam probe. It's like we will use for normal beam inspection, like if you see plate inspection, like plates, even for plates this kind of smooth. It's like if you say the beam is perpendicular to the surface. In case of now straight beam probes, it contains the single probe only. It will act as a transmitter and receiver. This is a TR probes. TR probes mostly we will use for thickness measurement, for measuring the smaller thicknesses. The advantage of this TR probe is it has a two different crystals. That one is will receive, one is transmit. One is transmit, one is receive. In case of this single crystal, we will use only single crystal. It will receive and it will transmit also the same crystal itself. But in this case, TR probe it has an advantage. It will receive individually. One crystal is dedicated for sending only, one crystal is dedicated for receiving. The advantage of TR probe is it will eliminate the dead zone. Like even for smaller thickness also we can measure using this TR probe. And one more is angle beam probes. These are mostly used for weld inspections. See, this is the basic angle probe design. The crystal is set at an angle so that it will deliver a beam at a certain angle. Generally, we'll have a like 45, 60, 70 degrees probes. Basically, in industry, 60, 70, 45 degree. These are the basic types of probes and their designs. And why we are discussing this different kind of probes? Selection of probes and frequency is very important for practical application or our daily inspections. That inspection capability depends on the different frequencies and different probes. So based on that, we have to select which probe is suitable for which application. So, and next slide is we'll say what are the different modes of propagations in ultrasonic waves. It's like a propagation of ultrasonic waves in a different waves. These propagations will helpful for real-time applications. First, we will come to know what is this propagations and what are the types and what is the difference in between. See, basically, we have like a longitudinal or compression waves, or transverse or shear waves. This modes has its own advantages. That's the reason we are discussing here how these advantages will benefit in real-time applications. We'll see in upcoming slides. And basically, if you see longitudinal waves or compression waves, the direction of propagation, the wave propagation, or particle movement is always parallel. The particle vibration is direction of the wave propagation. In case of transverse, is perpendicular. These are the particles, and this is the direction of the propagation. The particle vibration also is parallel to the direction of the propagation in case of longitudinal waves. In case of transverse, a similar way, but direction of the particle vibration is perpendicular to the direction of the wave propagation. If you see here, you see it will oscillate in a perpendicular way, like this. Here in this way is parallel way. And we'll see in upcoming slides what are the advantages.
Sorry for the inconvenience. There's some connectivity issue again. Trying to resolve it as soon as possible.
But your voice is not coming. मोबाइल का कॉल काटूं मैं पहले, कॉल काटता हूँ मैं पहले. Your voice is not coming by. Yeah. Okay, it's okay. Your voice is not audible.
हेलो
ये अपनी वीडियो मत
ऑन करो, वीडियो ऑफ रखो अपनी, ठीक है.
1 minute.
Okay, you are audible now.
Okay.
You are audible now. Okay, you can start. Yeah.
Okay. Thank you. Sorry for the interruption. Sometimes. These are the like different mode of propagations. We have seen like longitudinal and transverse, and one more mode of propagation is there like surface or relay waves. Especially this is we are using for measuring the surface indications. There is one example called long range UT. If you see in industries, basically we will use this kind of more convention for measuring the corrosion, any surface cracks in a practical way. The travel of the surface of the material and penetration to depth up to limited to one wavelength only, this surface waves. And compared to the longitudinal and shear waves, it has a less attenuated. Here we have to discuss what is an attenuation. Attenuation is nothing but a loss of energy when ultrasound is passing inside a material. When it is transmitting inside a material, suppose it is going for higher depth and all, it loses its energy. It loses some of its energy. That loss of energy is nothing but attenuation. It may happen because of dispersion. If energy basically it lost near to the grain boundaries in the form of heat in the form of scattering. That's called an attenuation. So plate waves, if you see this oscillation particles are an elliptical shape. If you see this block diagram, you can see an elliptical shape. So this different mode of wave propagations we will use in a different applications based on inspection scope. And one more is plate waves generated in a relatively thin substance whose thickness is less than the one wavelength. So basically we will use for lesser thicknesses only. Either it's like small tubes, small pipes which are less than the one wavelength. Because it exists many modes. It's like if you see the propagation of direction, it is like mixing of two. Like we can say it's a mixing of shear wave and translational waves. and it depends on the material thickness also, this wave propagation. Basically, what I'm trying to say, we have a different kind of mode propagations and it has its own advantages, and we will use this mode propagations according to the applications. Suppose if you see this upcoming slides, we'll see. Suppose we see this shear wave. Shear wave is basically we will use in weld inspection. Since it has a property, it has a property like it. While mode converting, we will generate the shear waves, as I have shown in the earlier picture. The shear wave we can generate like required our angles as per our inspection, and basically the shear waves are used for inspection of welds, plates, and pipes and tubes. But relay waves are nothing but a surface waves, especially used for inspection of like heat treatment cracks. It's like very minute cracks, fatigue cracks. These are very sensitive cracks. This kind of sensitive cracks can easily detected by surface waves. Surface waves are relay waves. Or plate waves are detecting of laminations in thin materials or bonding in composites. Basic idea is, so based on selection of these modes, we can use these modes for as per our applications. As I told, like inspection of welds, or detecting the fatigue cracks, or inspection of laminations in a materials, or any bonding issues. So that is the major applications. We'll see what kind of frequencies we'll use for upcoming applications. So we know mostly this wavelength and frequency and velocity are interlinked. So when you see, and if you see that penetrating power, it depends always on the frequency. When it is increasing the frequency, the penetration will decrease automatically. Since that lambda is decreasing. When you are going for lower frequencies, the penetration will increase in the material. Here is some example, the generally used frequencies for particular applications. We see 0.025 to 0.1 megahertz for ceramics and concretes. But since ceramics and concretes like very attenuated materials, we have to use low frequency only. Since low frequency means high penetration based on the instruction. So like 0.1 to 2 megahertz will use of plastic and rubber, cast irons. You say cast irons, we have a coarse grains. Coarse grains always leads to a more attenuated, more scattering. So we have to use a lower frequencies. So like 1 to 5 generally we will use for in steel sectors. Like for inspecting the roll bars or plates, we will use generally 1 to 5 megahertz. So depends on the thickness. So these are the basic frequencies, or these are the applications we will use generally these particular frequencies. So why I'm telling this, selection of frequencies play important role while inspecting a particular applications. So we should understand that how this frequency is to increase in the frequency, how this is detection, like increasing the frequency, how this wavelength is varying, and how this attenuation factor is influencing. This and all parameters are very important in the consideration of application point of view. So next, we'll see the different techniques. We have a different techniques in ultrasonic testing. It's like different techniques in the sense. So based on the probe arrangement, a probe setup, we have like a true transmission. One is pulse echo, and another is resonance. So like we have these techniques. Every technique has its own advantages. Every technique it has its own applications also. If you say true transmission, here if you see in block diagram, especially this method is for quality of the bonding in bonded composites. Why? So if you see the pulse echo, as I told, the same crystal will send the signal and will receive. But in this true transmission, we will keep transmitted separate probe and receiver separate probe. So the attenuation, even it will directly pass. It will transmit the signal from here to here. It will send and it will receive. In case of pulse echo, the same crystal will send it and will receive. So in this kind of during the signal interruption, we can easily find what is that what are any abnormalities are there or not. But the disadvantage, it cannot tell the flaw. It cannot. It can see here is this is the main limitation. Location of the flaw cannot be determined. Why? Since if any defect is there here, suppose this is a flaw, so that signal will not receive. If it is not receiving, you cannot see the defect signal here. The main purpose is to check this bonding only. It's not suitable for this detecting this flaws and all. And alignment of such unit create a problem. Generally, this is usual for this technique is usual for inspection of flanges of casting, assessing the quality of the bonds. Well, see the pulse echo. Pulse echo is the mostly used employed technique. Why? If you see radiography, everybody are aware that any other technique, it need an access. Suppose if you are going to inspect any object, it need an access, at least access from both the sides. In this case, if you see in pulse echo, it's not required an access. It's a single side access is sufficient. Since we are using the pulse echo technique, the same probe will send the signal and will receive. In case of, if you see in radiography, you should have access from the bottom also. Otherwise, you cannot perform it. Since that film, we have to place it. But that's the main advantage for pulse echo. Even if you see the thickness gauges and all, mostly in practical applications, you will not have access from the bottom. You have to take the thickness measure from the top only. They will open some insulation, the particular insulation. You have to take the thickness. In the particular case, this pulse echo most commonly used technique, and it will give the defect presence also and location of determination, and the single transducer it will transmit and receive. Suppose if you could see this block diagram, here is the crack is there. So suppose consider this a plate. When it is reflecting, this one is reflecting directly backward. When it is approaching to the crack, here you can see the crack echo. So based on the echo dynamics, we can say, and based on the time traveling, we can say, and where it is coming exactly, that crack indication on this time scale, and how much amplitude it is coming. And one more thing, if you see this initial pulse echo, but this initial pulse echo mostly we will observe in pulse echo technique only, since the same crystal is transmitting and receiving because of this. And next slide, and this resonance. It's all different techniques we will use based on the different applications. It's like if you see here this probe is sending the signal like a continuous longitudinal waves are transmitted into the material. The stand wave patterns form its materials. Actually, it's like we will fix for some certain frequencies. This frequency, when it is changing, like frequency is varying, then it's changing the resonance frequency. When there is a defect or any discontinuity, it changes the resonance frequency. So based on the resonance, we will find whether any defects is there or not. It will use to determine the thickness or quality of the bonding in the materials. So we have like for different techniques we will use according to our own applications. Like as I showed, like the two transmission we'll use for bond testing, or pulse echo for single axis thickness and defect detect location, and resonance for bonding characteristic for finding the quality of the bonding. These are the different techniques. And next slide we'll see the different methods. It's in the sense like in each medium we are using like different methods. Like one is the contact method, and second one is the immersion method. And in the contact method, we can say like a two beam of testing. So one is like normal beam of testing, one is angle beam testing. As I told you, normal beam testing probe is perpendicular to the surface and it will send in a straight path only. In case of angle beam testing, it will be in a certain angle. Suppose in the weld. In the weld on the top, we cannot do the inspection since it's an uneven surface and it will not propagate. So we will use the angle beam inspection. We will take the advantage of angle beam inspection in order to inspect the weld joints, welds. So it's like a weld ultrasonic angle beam inspection is basically it's like a trigonometry. Ultrasonic itself is a trigonometric. Once you know the trigonometry for weld inspection especially, you can play it as per our area of interest. We can easily see how this wave is generating at an angle, and based on that we will calculate the skip distances and so in what skip I had to cover this entire weld. So this is one of the advantages of angle beam inspection to check the weld integrity. This one is a metal workpiece, angle probe. This one is the flaw detector. This one is a depth. See, there is an example. See, lack of sidewall fusion. So this we will do based on the scan plan. We will design. So the scan plan will give you a proper, like we will design like it will cover entire build. Like that, we will design a scan plan. Based on the scan plan, we'll do the inspection for welding. These are the contact methods. So basically, contact method is we will contact with the object directly our specimen or weld or any job, particular job. Suppose in this case is plate, in this case is weld. We will keep our probe directly contact with the material. It's called contact method. If you see second one, immersion. But why we have to go for immersion? Yes, so we have a contact. Sometimes we have a irregular surfaces objects. So irregular surfaces in UT surface profile also very important. If it is uneven, we cannot contact properly. So you will lose the signal. So that is the main advantage in immersion. Immersion, even it is irregular, here we will use as a water as a medium. So even irregular objects also we can inspect properly in the, but some limitations are there that we will discuss clearly. So probe here can be avoided. It's like while if you see any contact, we have to move probe again and again. So it will abrasion will happen. It will damage the shoe also. But in this case, it's an advantage we are using in the water medium only. And component with irregular shapes can be easily inspected. It's a main advantage. Even irregular shapes also can easily inspected using this immersion technique. And speed also. If you see immersion, generally they do the C-scan. They will scan. It's automated. Once we start it, we can scan the entire surface and we'll see the entire sections. That scan waves we will discuss in a further slides. And the near field and dead zones can be eliminated since we have a gap. This gap is there. During this gap, we can eliminate this near field and dead zone. Dead zone is nothing like a blind zone where we are unable to detect the defect that particular zone. That's called. It can be automated also, but the limitations are. The limitation is it need a more medium. Like if you see larger objects, it's very difficult to do by immersion meeting. Such a complete immersion inspection is required, difficult to assemble components. Large amount of sound energy get reflected at water systems, reducing the indication amplitude. It is separately, we will generally use the immersion probes, like focused probes, and we will use different sensors, lenses to focus the beam, and we do the immersion testing. The main advantage is we need an containers like storage containers so that we will keep our inspecting sample and we do the inspection. Need a particular area. If you see contact method or any method, no need of any medium. We will use couplant and we'll do the inspection directly. But in this case, we need a water medium. You have to keep your sample inside the water medium. Suppose your inspected object may not be possible to dip it in the water. So in that case, then we have to see an alternative inspection. See, these are the initial pass, initial from the material. This one is the water delay, surface and drain back wall. If any fly is and these are the two different techniques. One is immersion, and one is contact methods. Here we have seen like what is the methods we are using. We will use for inspecting. Second one is equipment. Till now we have seen the fundamentals like what are the modes are presented and what are the techniques and what are the methods and what is an ultrasonic. But now we should know and we should aware about the equipment also. What kind of equipments and what are the equipments and how these equipments are useful for our desired specific applications. This we will discuss in upcoming slides. This equipment for ultrasonic testing is very diversified and selection is important to ensure the accurate inspection of the data as a desired specific applications. It's very important. We have like three components. One I have already discussed regarding transducer, like regarding different kind of probes, and we'll see the instrumentation. It's like different kind of we have ultrasonic systems like instruments. We have like dmeters and flow detectors. We'll see in upcoming slides, and calibration standards. How to calibrate this equipment? It's a very important. Since if you are doing the inspection without calibration, there is no use. Calibrating properly to standardize the equipment is very important while doing the inspection. Suppose, so as I told, you are using probe as a eye. If you are not calibrating properly, what will happen? The synchronization, equipment to the probe synchronization will not happen properly. It will not properly can see. It will not see properly. So if you want to see the properly that probe, you have to do the calibration. It's in a easy way. Just instrumentations. If you see, this one is the D meter, specially used for thickness measurements. So it contain only digital screen only. It will not contain any scan data. This one is the flow detector, ultrasonic flow detector. So Olympus epoch 600, I think. So ultrasonic equipment is generally we will purchase based on our inspection applications, and it may be a portable and stationary or immersion or automatic based on our requirement. Generally, if you see in our like a cross-country pipeline inspection, we will use automated ultrasonic testing machines. They are completely automated. Suppose for measuring the thickness, not enough automation and all. We will measure with thickness gauge also if it is allowable. If specification is required in a flow detector, we will use a flow detector. So basically, in instrumentation, we have different like say D meter, flow detectors based on the applications. So knowing this instrumentation is very important. What kind of flood detector we have to look, what kind of particular applications, what kind of equipment. Let's say we see the calibration standard. But why we need a calibration? Why can't we do without any calibration? Since many manufacturers will manufacture an ultrasonic equipments and everything, but we should know whether it is functionally working properly or not. So in order to not only working properly, in order to standardizing an instrument, we should do the calibration. So calibration is an operation of configuring the ultrasonic test equipment to known values. We'll have some standard calibration blocks. I will show in upcoming slides. So using the standard known values, we will check it whether this equipment is ultrasonic test equipment is working properly or not. It provides the inspector means of comparing the test signal to the known measurements. We'll compare with the test result with known measurements. And calibration standards come in a wide varieties of like different materials, but different materials are based on the inspection applications. But basically, the calibration standards are typically manufactured from the same material only. Same material, same acoustic properties. It's very important. Suppose we are going to inspect in carbon steel. We will use carbon steel calibration blocks only, or aluminum. We will use aluminum calibration blocks only. Since that acoustic property should match, that's very important. So it will give the realistic values, realistic inspections. And we'll see upcoming slides. So some of the typical standards. These are the calibration standards. We will use this is for using measuring the thicknesses. This one is the step base. Generally, we do the calibration using the step base for measuring the thicknesses and all, either for demeter or flow detector also. This one is the IAW International Welding, like this IAW V1 block. This one is the V2 block. It has all dimensions that we'll see. See that every calibration blocks has its own advantages. It has designed in a beautiful way so that we can check our equipment whether it is working functionally proper or whether it is detecting our inspection requirements or not. If you see this V1 block, it is designed like it has a 100 mm radius and 300 mm length. We can do the range calibration, lot of like many calibrations using this one, but it's little heavy. When it is coming to the V2 block, it's a very portable block. It's small block only. Thickness is 12.5 mm, but it's very easy to carry everywhere. It's like in service inspections and all. We used to carry for weld inspection. We used to carry V2 block, so that we can check the angle, what angle, whether probe angle is coming properly or not, or otherwise we will change it, or this hole sensitive for measuring the probe index. It's like a portable calibration block. It's in order to stand before proceeding the inspection, in order to stand as our equipment for angle beam inspection. So generally here, as I told, I have discussed normal beam inspection and angle beam inspection. One more most important point why we are using angle beam inspection is that suppose the defect is like perpendicular to the weld, it's okay. But if it is a parallel to the probe, so in that situation, normal probe inspection will not detect. So in that situation, we will use angle beam so that it will incident beam will strike perpendicular to the surface of the indication. So always in ultrasonic testing, it should be hit to perpendicular. Then only it will reflect back with the sample, in the indication. So in that particular application, we will do the angle beam inspection. So that effect is oriented in a different angle. We have to use the different angle beam probes only, angle beam inspection only. In normal beam, we cannot detect any oriented defects. These are the calibration standard DAC blocks, and this one is the ASME pipe calibration blocks. This one are like we will put in known defects like either sidle hole or notches based on the specification. So in case of ASME pipe, so when we are doing initially we make the calibration blocks using EDM notch. Like we consider two notches. One is top notch and one is bottom notch. And based on this notch, we do the calibrations. Whether this specification is customer what they do generally in pipeline industry, when we are going for an inspection, they do the validation. First we do the calibration, after that validation one will be there. So the validation is the known defects they will give. Before doing this calibration, while doing the calibration, we have to use these blocks in order to standardize our equipment. This one is DAC. DAC is like distance amplitude correction that we do. Suppose, for example, when we are going for higher depth, as I told, attenuation issue will come. But even if you are going higher depth, the same defect signal, suppose consider 2 mm, 1 mm sidle hole. So I made a hole in a different depths. Suppose one is at 5 mm, one is at 10 mm, one is at 15 mm, for example. But the defect size is 2 mm only. Suppose when I am detecting any depth, I have to find only 2 mm depth only. But if you are not doing DSC, distance amplitude correction, that correction is happening because of the attenuation only. If you are not doing the correction, it will show different sizes. In order to avoid that amplitude, we have to do the amplitude correction by using the DSC blocks. Okay, or to nullify that attenuation, effect. These are the basic calibration standard blocks, and this is the qualification standards. Basically, qualification standards are different from the calibration standards in their use. The purpose of wearing the proper equipment operation and qualification of the equipment. So every code like IAW, American Welding Society, every entity has this board like standards, qualification standards. Basically, it will check the calibration. It will check the proper equipment operation, like equipment operation, how this equipment is working. Suppose sometimes you don't know that out of calibrated equipments also will do. When you are checking it, you can easily find, when doing the calibration itself, we can find something issue with this equipment. Since it is not calibrating properly, something issue with this manufacturing calibration or something issue with the components, either maybe by checking the standard calibration blocks or qualification standards only. And every this qualification has its specific codes and standards. These are the basic blocks. This one is the resolution blocks. Will try to find this whatever we are using flash detector, whatever it may be, whether properly resolving or not. This resolution is very important. How well it is resolving the defects, closed defects. And beam profile, how this profile is it's like every stage not judging your capability of equipment. So either it's a beam, either it's resolution, either it's the range, whether properly it is penetrating or not. It's sort of like standardizing our equipment only. That's basic idea. Second is applications. And what are the major applications in ultrasonic testing? If you say flaw detection is one of the most important in oil and gas industry and everywhere. And arrows, see crack detection and inclusion and porosity. But this cracks and all will get in very high reflection peaks. But inclusions and porosities like echo dynamics, we will get in a porous kind of signals. In sharp, you will get for lack of fusions and cracks. For inclusions and porosity or slag inclusions and all, you will get a porous signal. Erosion, erosion and corrosion thickness gaugings, especially if you see like elbow or any elbow or any like pipe connection. If you see they are prone to the erosions. That and all we can measure using ultrasonic testing, like a corrosion mapping. We do the corrosion mapping, how much percentage corrosion is happened. We have different techniques we will use, like assessment of bond integrity in adhesive joints, as I discussed, one of our advantages applications, measurement of case hardening depth, and in other applications also, like long range ETA, as I told, long range ETA. And we'll see that real-time applications. Thickness gauging is one of the most important application we will use in every regular applications, every application. Suppose if you want to know, if you want to suppose generally they do the survey thickness or corrosion mapping survey. They do the thickness gauging. They will measure every elbow or every pipe. They will check like three. Suppose you take the pipe, in the pipe how they will measure. They will measure 4 points like 90 degree, 90 degree, 90 degree. They do the averaging. Suppose where the minimum thickness is coming, they will knock down. So they do the plant survey. So every entire plant pipe thicknesses, they do the thickness gauging. So based on the thickness gauging, they measure how much time it will take for reducing the for estimation of the life of that pipe. They will estimate. It's like a condition. They do the monitoring. Like every year they do the survey. That's one of the applications. So applications including a piping systems, storage or pressure vessels. Basically, it's a petrochemical application or utility industries, various degree of corrosions. If you see in the example, this one is ultrasonic probe. Here is the corrosion loss is there. So this we can see in echo dynamics. You will get a porous signal. You will get like a zigzag kind of signal, and any laminations, thickness gauging. And second application is flaw detection. As I discussed, flaw detection in wells is very important. Weld integrity, whether any abnormalities or any lack of fusion, porosity, or any slag, or any root fusion issues. This and all can be easily detected using using angle beam inspection. It's mostly widely used in weldment, inspection of weldment in ultrasonic inspection. And full penetration of groove leads to readily angle beam examination. Basically, while we do two kind of there, using the in angle beam inspection, we can take the normal probe only. We do the mode conversion, like using the wedge angle cutted wedge. This is one, and one more is directly shear wave crystal. We'll take the crystal itself, the directly shear wave crystal, based on the applications. These are the most widely used method of inspection weldments. Second one is, these are the advantages. So like as I told, one of the advantages, most important advantages, only single side access is needed when falsetto technique is used. No need of both side access. That even if there is no access from the bottom, we can easily do with this pulse echo technique. And high accuracy in determining the reflector position or estimating the size of the shape is very important. We'll get an accurate size approximately, determining the position and for which depth it is coming. Suppose it is coming at 5 mm or 10 mm, we can measure it, the depth or size of the indication. So what is the length of a crack or length of an indication approximately. And minimum part preparation is required. This is true actually. If you see other testing equipments, even radiography, you need a lot of preparations and all, or either any other techniques, but especially in ultrasonic, we need only a single side access. Or if it is an insulator, you have to remove so small insulation we have to do, or any normal pipe, like partial minimal part preparation is required. And sensitive to both surface and subsurface. It's like mostly you can do subsurface and internal defects also. And penetrating capabilities, it has superior capabilities than other methods. And you will get a real-time images. If you say in radiography, generally in film radiography, actually, you have to capture the on film, again you have to interpret the film. But in this case, you can see the digital image directly. And you can store that image also, like it has a capability, and you can make an automating system also using the ultrasonic. These are the some of the advantages and some of the limitations. Some of the limitations, as I told, the surface must be accessible to the transmitted ultrasound. So one of the, it should be accessible. And one more important is like, as per my experience, especially the theoretical knowledge, as per me, it will useful for every extent time, but troubleshooting and practical experience is very important in non-destructive testing. So if you see, so when I was working, we used to encounter many issues like it will not properly counted while inspecting. Either you should understand immediately where the issue is happening. Either is from probe, either is from any wire, or either issue from the calibration. This and all will come by practical exposure. Skill and training. Skill and training is more comprehensive than other methods. Extensive skill is required and more understanding is required. And normally required a coupling medium to promote a transfer of sound. As I told, a couplant kind of medium is required for ultrasonic testing. And cast irons, and like if you see cast irons and austenitic stainless steels, these are like a coast grain structures. These coast grain structures are really difficult to inspect due to low sound transmission or or more attenuated materials. So high signal to noise ratio, or you will get asymmetry, like scattering issues in coarse grain materials, especially this grain boundaries, a lot of heat dissipation. The more grain size, the more grain size, the a lot of heat will generate and a lot of energy will lose. And and one more thing is reference standards are required for both equipment calibration and characterization of loss. Yeah, it's very important. But we will do an artificial defects which are like closely it will give maximum. The way we do we will do the calibration. While doing the calibration, we do like artificial defects, or while validating also we do artificial like notches and signing off. It will approximate detection, but always whatever we are detecting defects are always will get a higher signals only. So there will not be an issue. The second one, yeah, up to here we have seen the advantages of applications and limitations, and two more techniques are there, like so this and all advanced techniques like phase array ultrasonic testing. Till now I have discussed like a conventional way only, like single crystal or dual crystal we are using. That we are doing the inspection. But if you see in advanced techniques, suppose if you want to inspect a weld, you have a 3 different kind of angle probes like 45, 60, 70. But you have to, if you're using, if you want to use an particular angle, you can use only particular angle only. You cannot use 70, 60 at a time in a conventional. But in phased array, it's an advantage. You can use a single, like it contains an array of probes in a single probe, array of crystals. You can alter. You can get a required angle based on the time delay. It's like completely powerful electronics. If you see here in this one is the probe. We have made and set up in a normal scan. Here is the 3 sidal holes. You can see the 3 sidal holes clearly, 1 and 2. This one is the scan side view. Like here you can see scan. These are the different views. Like top scan, like top view is called C scan. Side, this one is the D scan. This one is the B scan, like this cross section. Cutting of the sample is called B scan. So the main advantage is no need to use a special, no need to use the individual angles, and it will provide the real time images. And one of the advantages, we will get a confident while interpreting the defects. We can see the possibilities and we can see the orientation of defect, how it is oriented, and we can measure the accuracy and sizing also, and real-time imaging. It is an advanced NDT technique used to set up the ultrasonic probes made of numerous small elements. It will contain an array of elements, like generally 64 elements or 128 elements based on the inspection. But little costly, and but its advantage is you can get a real-time image. Real-time. If you see in conventional UT, you will get an A scan only one scan, A scan, one echo, one pulse, one indication. But here you can see the all views, like C scan view, B scan view, so that you can estimate the orientation of the defect in a proper way. And each of these pulses, and the basic phenomena is like Heisenberg principle. It will work on Heisenberg principle. And basically, how we are changing these angles based on the delay. We will fire each crystal in a particular delay. It has a powerful acquisition unit. Generally, in our market, we will use like Olympus, Omniscan MX2. It's mostly oil and gas industries will use this PAT equipment only for fast inspection and fast justification of the defects. And these are the basic views. If you see, this one is the B scan and all. And one of the advantage we can easily judge it whether it is a slag inclusions or any porosities. We can see the clear picture, clear image, or accuracy sizing, and it depends on the amplitude reception only. Phase array ultrasonic. So like basic idea is like compared to the conventional, it has a array of crystals. It can easily change as per our requirement, as per our required angles. Suppose some the main advantage, like in that particular conventional case, we will use the one single angle only. Suppose your defect has a multiple directions, like a defect has in multiple orientation. Here we have a set of angles so that it can measure the different oriented defects. And this one, the last slide, time of flight of diffraction. This is one of the advanced technique, which is basically used to do the proper, like accurate sizing of the defects, especially vertical defects. If you see this kind of vertical defects can be accurately sized. Why? Because it's not depends on the amplitude. It depends on the tip diffraction. So tip diffractions, here one diffraction will happen at the top tip, so bottom tip. If you see, so sizing is based on the time of arrival of the defect, not on the amplitude. Amplitude based all of PAVT and conventionality. This is completely on diffraction only, tip diffraction, and it will give the accurate sizing. So using these both techniques like PVFT and PAVT, we can accurately detect the defects and we can accurately size the defects. And this setup generally used in oil and gas industries for inspection of pipes. You see lower signal. This one is the tip signal, upper tip signal, and this one lower thickness. So based on this time scale, we can measure the how much length is this one, and this is the B scan gray scale. and we can see how much depth it is coming, how much length it is. We can measure accurately. Okay, these are the techniques. Basic. Initially, we have seen the NDT, any different methods, and what are the techniques and advantages and applications, and the real-time applications and instruments, and the advanced techniques like TVFT and PFT. Okay, thank you.
Thank you very much for Tataji giving you this information regarding this lecture. Participants can ask the question if you have some queries. Participants can ask the questions if you have queries. Anyone is there?
Thank you, sir. Thank you so much.
Thank you so much, madam.
Thank you, Tataji.
Thank you, Mr.
Thank you, sir. Thank you.
Thank you so much.
Thank you,
boss.
participants, for your cooperation and patience, as there was a connectivity issue on speaker's side during the session.